Okay, so last class we have discussed about the theory of angular momentum in quantum mechanics. When the particle is moving in a straight line path and that particle is associated with the linear momentum p, and the same particle when it moved to the circular path and it associated with the angular momentum and it written as capital L. And based on that concept, we have also discussed the angular momentum algebra, and I'm giving a summary of that one. Suppose if the component of L, say Lx, Ly, Lz, if it commute with each other, then we can get it La plus Lb. If it commute, then we will get it I H cross. This is a Levi-Civita tensor and leads to a third component Lc, angular momentum. So here this Levi-Civita tensor is equal to 1 when the ABC is making a cyclic permutation A, B, C, B, C, A, C, A, B. This will be 1 and it will be minus 1 this if it is non-cyclic permutation. And otherwise it is 0. Suppose if any two of the indices is equal to one another, say example A equal to B or B equal to C or C equal to A, then this tensor value will be 0. So this is a first point. And second point, the operator, two operator we have discussed. One is called L plus a raising operator and L minus lowering operator. These two are the non-Hermitian operators. If it is commute with each other, L plus L minus, we will get it 2H cross L Z. And the third point, suppose the component of L, say example Lx, Ly or Lz, commute with this raising or the lowering operator Lx, if it is commute with the raising operator or the lowering operator, so we will get it minus plus H cross Lz and Ly, L plus minus will gives as minus I H cross Lz. And Lz commute with the non-Hermitian operator L plus minus will gives plus minus H cross L plus minus. The fourth point is the component of L, say Lx, Ly or Lz, if commute with the total angular momentum L squared, say example I am writing Li and commute with L squared, total angular momentum. Here I equal to x, y, z, anything will be 0. Then fifth point, when the total angular momentum commute with the non-Hermitian operator L plus L minus will be 0. So this 5 point we have discussed in the last class. In continue to this particular class, we are going to discuss the state vector and quantum numbers associated with angular momentum in quantum mechanics. And fine, state vector and quantum number associated with angular momentum in quantum mechanics. Let us first actually take a total angular momentum L squared and it associated with the quantum state, say example the quantum state vector is nothing but A, and the angular momentum along G direction and it associated state vector we call it Z. The combined state vector, if we write for this both of this operator, then we can write it A comma Z in state vector A comma Z. Here A is a state vector associated with the total angular momentum and Z is the state vector associated with the angular momentum along G direction. So example, a state vector Z arbitrarily we are taking in this way, and this is actually angular momentum in G direction is here, and if the raising operator or the lowering operator acts on this state vector L plus acts on this state vector, arbitrary state vector Z, it will give as some constant, some eigenvalue, then G plus H cross. G plus H cross. If suppose the lowering operator L minus acts on this state vector, then it will give eigenvalue Z minus H cross. That means if L plus acts on Z vector, it will move up to one quantum level G plus H cross. If L minus acts on this state vector G, then the actual state vector will move down to one quantum level H cross, and our aim is here to find out the total angular momentum, to measure the total angular momentum due to L plus acts on Z vector or G state, and L minus acts on G state. And what is the effect of total angular momentum? So that is first concept. Second concept, we want to measure the angular momentum along G direction due to L plus or L minus acts on this eigenstate Z here. So there are two concepts. First we will actually discuss the total angular momentum, the effect of total angular momentum due to L plus and L minus acts on eigenvector Z. So mathematically we can write that one, operator, total angular momentum operator, say example L plus or minus operator acts on this combined state A, Z. So further we can write L plus minus A, Z. So you first consider the raising operator. Acts on this eigenstate, and what is the result in total angular momentum? For writing that, L square L plus A, Z eigenvector is nothing but L square operator L plus operator A, Z. But what is the value of this product L square and L plus operator? So first take the commutator relation. L square with L plus is nothing but L square L plus minus L plus L square, and this value will be 0. So we can simply write further L square L plus is L plus L square. Now we can feed this value from here to this equation. So L square L plus A, Z is equal to L square L plus A, Z is nothing but, this is nothing but, we can write it L plus L square A, Z. Again this equation L plus L square A, Z, you put one bracket here. Now the L squared operator, as I already said, L squared operator, total angular momentum operator, associated with the state vector A. So if this operator acts on this combined state, will give you a eigenvalue, say A, and A comma Z. So actually we don't know the real value of A. Right now you keep it. The eigenvalue when the total angular momentum acts on the state vector A will give you the eigenvalue as A. But we need to determine the actual value of A later. So further we can actually, A is nothing but a number. You can take outside L plus A comma Z. So this is nothing but L square L plus now let's see the effect of total angular momentum L square due to the lowering operator acts on this state vector A comma Z. Square L minus acts on the combined state vector, this one. Further can be written this one L minus A comma Z. Now we have to find out the product of this L squared L minus. For that you take it the commutator relation L squared with L minus, and that value is nothing but L minus minus L minus L squared. Again this is also gives as 0. Then from this relation we can write it L minus is nothing but L minus L squared. Now if we feed this information from here to here, then again I am writing this expression L squared L minus A comma Z equal to L squared L minus A comma Z is nothing but L minus L square A comma Z. So this expression I am modifying as per my convenient with one bracket. So now this L squared operator acts on this state, as we already discussed. This vector state vector A is associated with the total angular momentum. If this operator acts on this state, will give us a eigenvalue of A comma Z. State will be retained. A is nothing but here a number or eigenvalue, so we can simply take outside, there is no problem. So L minus A comma Z. this is nothing but L square L minus A comma Z. If we are combining these two expression here, this one and this one, we are combining these two expression, we can write it L square L plus minus a state vector is nothing but A L plus minus A comma Z. If we look this expression, it's clearly telling us that the eigenstate of a total angular momentum operator, eigenstate, this is nothing but eigenstate. Eigenstate of the total angular momentum operator is L plus minus A comma Z, and the eigenvalue of this total angular momentum operator is A. Eigenvalue. Fine. Now, the second objective, the effect of angular momentum in g direction due to the raising operator and lowering operator acts on a state A comma Z. We are measuring in g direction. The effect of angular momentum along z direction due to raising operator or the lowering operator acts on this state vector. So, first for considering the raising operator, we will write L plus A comma Z. Is nothing but LZ L plus operator A comma Z, a state vector. Now we need to find out the product of this LZ and L plus. For that, you take it the commutation relation LZ L plus if it commute with each other, then LZ L plus minus L plus LZ. Then, so LZ you write it, but L plus we know that Lx plus I Ly. Similarly, minus L plus we know that Lx plus I Ly Lz. If you multiply Lz inside, then Lz Lx plus I Lz Ly for the first term, and for the second term Lx Lz, one negative sign is outside, so minus I Ly Lz. Now if you combine the real part and imaginary part separately, so Lz Lx, then here minus Lx Lz is there. Fine. Then coming to the imaginary part, take it I outside. Minus I Ly Lz, then you bring this term here Lz Ly, because minus I, if you multiply with this term, you will get here this negative sign, and this negative sign will become a positive sign with I Lz Ly. Fine. Now this first two term is nothing but, according to the quantum mechanics algebra, Lz Lx, commutation of Lz Lx will give Lz Lx minus Lx Lz. So minus I, here if you come here, this is actually a cyclic permutation. So Z followed by X, but here this is a this is also a cyclic permutation, so there is no problem. So then here we can write it Ly Lz commutator, Ly Lz commutator. So Lz Lx is nothing but I H cross L Y, and Ly Lz is also I H cross Lx. If we feed these two terms here, so we will get it Lz L plus commutation is equal to this one I H cross Ly, I H cross Ly, and this term already one negative sign is there, one I is also there, this will give you I H cross Lx. So this one is nothing but I H cross Ly. So here one negative sign, I multiplied with another I square become my negative sign, so here plus sign, so it will be H cross Lx. Then this is nothing but, we can further modify this expression by taking H cross outside, then Lx plus I Ly. So Lx plus I Ly is nothing but H cross L plus. So this is nothing but this one I am writing. So Lz L plus minus L plus Lz equal to H cross L plus. From this expression we can find out the product of Lz L plus. So Lz L plus equal to, you keep it H cross L plus here and take this L plus Lz with negative sign from here to this side, it will become positive sign. Now if we feed this information from here to here, so Lz L plus A comma Z is equal to L plus Lz plus H cross L plus A comma Z state vector. Now if you multiply state vector inside this term, so we will get it Lz A comma Z plus H cross L plus this one. Now we can make it L plus Lz with bracket A comma Z plus H cross L plus A comma Z. So this Lz, as I said, the state vector Z is associated with Lz operator, angular momentum along g direction. So if this operator acts on this state, then the state vector Z only will be affected. Then we can write this one as L plus with the eigenvalue of Z. When Lz acts on this state vector, it will give the eigenvalue as Z. Then state will be retained plus this term remains same. Now if we are taking Z, as we already discussed, Z is nothing but the eigenvalue is a number, we can actually constant number, we can take outside, there is no problem. So Z L plus A comma Z plus H cross L plus A comma Z. Oh, sorry. So this one should come here. Further, if this is the common term for the both the place, so we can actually take it Z plus H cross, Z plus H cross, this is a common term, L plus A comma Z outside. Fine. This is actually the effect of raising operator acts on state vector A comma Z. Suppose the angular momentum effect Lz along z direction due to the action of L minus on A comma Z. So mathematically can be written in this form. So L minus A comma Z, the effect of angular momentum along g direction due to the lowering operator acts on a state vector A comma Z. So further this expression can be written L minus operator A comma Z. Now we have to find out the product of these two terms, Lz and L minus. For that we had to take the commutation relation of Lz L minus is nothing but Lz L minus minus L minus Lz. So we know very well Lz and L minus is nothing but Lx minus I Ly minus Lx minus Ly into LZ. If you take the product, then LZ LX minus I LZ LY, this term product with I LY. Now LX product with LZ with negative sign, LX LZ. Then further here one negative sign, another one negative sign is also here, so it will become a positive sign, LX LZ with I term, imaginary term. Now we are grouping the real term and as well as the imaginary terms. So LZ LX minus LX LZ and the imaginary terms here, oh, this is I think LY. Okay, so put the bracket here, I, so LY LZ minus LZ LY. So first take this term, first take this term LZ LY, then LY LZ. Now if you multiply with a negative sign, it will become positive sign, with I you will get this one. Okay, fine. So now according to the angular momentum algebra and commutation relation, so we will get LZ LX minus LX LZ is nothing but LZ LX commutator minus I LZ LY commutator. If you look here, then Z followed by X, it's a cyclic permutation, and here minus I LZ LY is a non-cyclic permutation, so we can write it I H cross, this one is nothing but LY, and when we come here minus I, so this is a non-cyclic permutation, so it will give you minus I H cross LX. So negative sign will come due to the non-cyclic order. Now I H cross LY, here there is already two negative sign and I square will give minus 1, so minus H cross LX. From this expression we can take one negative sign outside and H cross LX. So now we will get, if you multiply minus H cross LX, then we will get this one, then minus I LY, this term is coming. If you multiply minus H cross inside, you will get this term. Fine. Further we can reduce this expression LZ L minus A comma Z state vector is nothing but minus H cross. So we know LX minus I LY is the complex conjugate of L plus, that is nothing but L minus. If we are writing together, then L is at L plus minus A comma Z is nothing but plus or minus H cross L plus or minus. No, there is a problem. No. So here this is nothing but so this term is nothing but equal to this one. L is at L minus L minus L is at is equal to minus H cross L minus. Then we can find the product of this L is at with L minus from this relation. L is at L minus will gives as L minus L is at minus H cross L minus. Now if we feed this expression from here to here, we will get L is at L minus A comma Z is equal to L minus L is at minus H cross L minus with state vector A comma Z. Now if you multiply L minus L is at with the state vector minus H cross L minus A comma Z, further we can write it L minus L is at with bracket A comma Z minus H cross L minus A comma Z. L is it here. So earlier also we discussed the state vector Z is associated with the angular momentum operator along G direction. Suppose if this operator acts on this state vector, it will give the eigenvalue of Z. Then put it L minus, if this state vector acts on this state, this operator acts on this state, will give a eigenvalue Z. A comma Z state will be retained minus H cross L minus A comma Z. Further we can rewrite this term because Z is nothing but a number, we can write or we can take outside that one. L minus A comma Z, put the bracket, minus H cross L minus A comma Z. So L minus A comma Z is the common term for this expression. So we can write it further Z minus H cross, if we are taking outside L minus A comma Z. This is what the angular momentum effect of angular momentum along z direction due to lowering operator acts on a state vector a comma z. By combining both the raising operator and the lowering operator, we can write L is at L plus minus a comma z, a state vector, is nothing but z plus minus h cross L plus minus a comma z. Okay, if we look this expression here, this expression again, L plus minus a comma z is nothing but eigen state of Lz vector. And z plus minus h cross is nothing but eigenvalue of Lz vector. Now we are writing the effect of total angular momentum and angular momentum along g direction due to L plus minus acts on a state vector a comma z. Okay, so L square L plus minus a comma z we have already discussed. So eigenvalue L plus minus a comma z it gave, and the effect of angular momentum along z direction due to raising operator and lowering operator acts on the state vector will give as h cross g plus minus h cross L plus minus a comma z. So point number 1 here, as we discussed, this is eigenstate. L plus minus a comma z is a common eigenstate. Eigenstate of total angular momentum operator and the angular momentum along g direction. It's a common eigenstate for both of these operators, but the eigenvalue of total angular momentum is a, and the eigenvalue of angular momentum along g direction is different from the total angular momentum, z plus minus h cross. So suppose if we are considering the common eigenstate, this is actually a common eigenstate for this 2 operator, and we are taking this common eigenstate L plus minus A comma Z and L plus or L minus acts on this state vector affect only the G state. It do not affect any A value because A is associated with the total angular momentum and G is associated with the angular momentum along the G direction. So this will actually produce, if L plus minus acts on this state vector, this will produce some eigenvalue and L plus acts on Ez, it will be moving up one quantum level. If L minus acts on Ez, that Ez vector will move down one quantum level. So we can write it Ez plus or minus H cross with some eigenvalue. We don't know what is that eigenvalue, we need to determine. So right now we can write it, the eigenvalue as A comma Ez is nothing but C plus minus A comma Ez plus H cross. Fine. So probability constant C plus minus is nothing but probability constant. Now take the LZ operator on both sides of this expression. So L plus minus A comma Ez equal to LZ operator C plus minus A comma Z plus minus H cross with bracket. Here C plus minus is nothing but a constant, so again we can take outside. So LZ A comma Z plus minus H cross. Again, this state vector Z plus minus H cross is associated with the angular momentum along G direction. If this operator acts on this state, it will produce a eigenvalue if LZ acts on this state, will produce the eigenvalue G plus minus H cross and state will be retained A comma Z plus minus H cross. But the value of C plus minus A comma Z plus minus H cross is nothing but L plus minus A comma Z vector. So Z plus minus H cross, this one will be replaced by using this expression A comma Z. So LZ L plus minus again we are proving the same expression here, what we have done already. Okay, so Z plus minus H cross is nothing but the eigenvalue of LZ operator, and L plus minus A comma Z is nothing but the eigen vector or eigenstate of this LZ operator. Fine. Suppose if we are taking L square operator on both sides of this expression here, then L square L plus minus A comma Z is equal to C plus minus A comma Z plus minus H cross. L square operator is missing. L square C plus minus A comma Z plus minus H cross again. The value of C plus minus is nothing but a constant. The constant of probability can take outside C plus minus. So L squared operator, yeah, ket vector A comma Z plus minus H cross, ket vector, state vector. As we already discussed, the total angular momentum operator is associated with the state A or ket A in this combined state. Then that will give the eigenvalue of A C plus minus A comma Z plus minus H cross ket vector. Again, the value of C plus minus A comma Z plus minus H cross is nothing but L plus minus A comma Z ket vector. So we can replace this one A with this value L plus minus operator A comma Z is nothing but L square L plus minus A comma Z. Here A is the eigenvalue of the total angular momentum operator L square, and L plus minus A comma Z ket vector is the eigen state of total angular momentum operator L square. Again we are proving the same by using this method. Fine. Now we have to determine the actual value of this A and Z. What is the actual value of the eigenvalue of A and Z? For this, determine the value of A and Z. for determining the value of A and Z, take the product of L plus L minus. So we know already the raising operator L plus is associated with Lx plus ILy, and the complex conjugate of L plus is nothing but L minus. So Lx minus ILy. Now if we take it L plus L minus, here Lx plus ILy, Lx minus ILy. Take the product Lx will give Lx square, this two product. Now I am coming to this two term. So I here minus I, so I squared will give you one negative sign, already one negative sign is there. So it will be positive sign Ly square. Now take it Lx with this ILy with a negative sign. So minus I Lx Ly, and now you take this two term, product of this two term will be plus I Ly Lx. Fine. Lx square plus Ly square, here take it one negative sign and I also outside, Lx Ly minus Ly Lx in bracket. So if we multiply minus I inside, we will get this term. So Lx square plus Ly square minus I Lx Ly minus Ly Lx is a commutator, will give as Lx Ly commutator, and value of this one Lx square plus Ly square minus I h cross Lz. Again L plus minus is equal to Lx square plus Ly square. Here already one negative sign is there. If this product of 2I will give you I squared as minus 1, then this will be positive sign h cross Lz. But the total angular momentum is written in terms of L square as Lx squared operator, Ly squared operator, Lz squared operator. Then here if we look, Lx squared plus Ly squared operator is equal to L squared operator, and take this Lz squared operator from this side to this side, and it gives negative sign. If we feed this value from here to here, then L plus L minus is nothing but L squared operator minus Lz squared operator plus h cross Lz operator. This is very important term. Fine. Now you take the a combined eigenstate on both sides of this expression. Take A comma Z, a combined eigenstate on both sides of this equation. L plus L minus A comma Z is equal to L square minus LZ square plus H cross LZ. Get A comma Z. Now multiply inside. L square A comma Z minus LZ square A comma Z plus H cross LZ A comma Z. Again, this expression or this expression can be rewritten L square equal to L plus minus, this term is coming here, LZ square minus H cross LZ square. Now take the combined eigenstate on both sides of this expression will be L square A comma Z L plus L minus plus LZ squared minus H cross LZ A comma Z. Now if we multiply inside or just keep it as such, then we will do. L plus L minus A comma Z plus LZ square A comma Z minus H cross LZ A comma Z. Now apply Z goes to Z minimum. This is the lowest level of Z. Further, we don't have any more level below than the Z minimum. So this is a Z level. Say example, and if L plus acts on this, we will get a new state Z plus 1. Again L plus acts on this particular state, we will get another new state H cross, this is 2H cross, it will go like this, and this is called Z maximum. Further above this we don't have any state vector, we cannot move beyond this state. And similarly, if the lowering operator acts on this G state, then we will get it Z minus H cross. Again, if it is another lowering operator acts on Z minus H cross state, we will get Z minus 2H cross. Similarly, if continuously the L minus acts on here, we will move up to this G minimum. So below this state we don't have any energy levels. So this is the lowest energy level and this is the highest energy level. So below this we don't have any energy level, and above this also we don't have any energy level. It's completely vacuum state. Not a vacuum state, it's a vacuum, completely vacuum. So suppose if we are applying G goes to Z minimum in this expression here, then we can write this expression as L square operator A comma Z minimum is equal to L plus L minus A comma Z minimum plus L Z square A comma Z minimum minus H cross L Z A comma Z minimum. So suppose this either the lowering operator or the raising operator, if it acts on this state, a combined state. Here first the lowering operator acts on G minimum followed by raising operator. So lowering operator first acts on G minimum, this will give 0 because further we cannot actually lower down anymore. L minus acts on Z minimum will give as 0. Further we don't have any energy level. We cannot further reduce or go down below this G minimum. So if L minus first acts on G minimum, it gives 0. Then if this term is 0, then the entire term will be 0. Then only we have this two term only, Z minimum equal to, this is 0 plus L Z square A comma Z minimum minus H cross L Z A comma Z minimum. So this L Z operator acts twice on this state A comma Z minimum. Then we can write it L Z A comma Z minimum minus H cross L Z A comma Z minimum. So first this L Z acts on this state and this L Z acts on this state. Let's see what is coming. So L Z, you keep it, the first L Z, and So first operator, this operator only acts on this, followed by this operator acts on this. So if it is acting on Lz on this state vector, will give some eigenvalue, that is nothing but z minimum and a state vector retained, z minimum minus h cross, here again another g minimum, a comma z minimum. But the term is not completed. Again one more Lz operator is here. So this g minimum is nothing but a constant or the number we can take outside, and this Lz further will actually operate on state vector a comma z minimum, will give as z minimum square a comma z minimum minus h cross z minimum a comma z minimum. Now the state vector a comma z minimum is common for both the term, we can take outside, then z minimum square minus h cross z minimum in bracket a comma z minimum. So this is nothing but L square a comma z minimum is z minimum square h cross z minimum a z minimum. I am just rewritten again. But if this total angular momentum operator acts on this state vector, will give a eigenvalue with a comma z minimum is equal to z minimum square minus h cross z minimum a comma z minimum. Now if we compare this equation on both sides and to remove the state vector, the value of a, actual value of a is nothing but z minimum square minus h cross z minimum, or we can write it z minimum minus h cross. This is nothing but the value of a if we are considering the value of state vector g is as z minimum. Suppose if we are considering z as g maximum, then all of this z minimum is become the g maximum. I am writing that one, a comma z maximum, but here this term will be different. So for that better to now for finding the value of a by using g equal to g maximum, we have to take the product of L minus L plus first. Lx minus ILy, Lx plus ILy. So take the product L x square, L y square, this two product. Now you come with this I Lx Ly. Now here with this one, this two. So minus I Ly Lx. Further we can reduce Lx square, Ly square plus, take the I outside, Lx Ly minus Ly Lx. This is nothing but Lx square, Ly square plus I. This is the commutator relation Lx Ly, and this is nothing but I h cross Lz. If we place it here, I into I square minus 1. So L x square plus Ly square minus h cross Lz is nothing but L minus L plus. But the total angular momentum operator L squared is written as Lx squared plus Ly squared plus Lz squared again. Then if we feed this value Lx squared plus Ly squared again, L minus L plus h cross Lz is nothing but Lx squared plus Ly squared. If we feed this value here, then this term L squared is nothing but L minus L plus h cross Lz plus Lz square operator. Now you take the state vector A comma Z on both sides of this expression, then is nothing but L minus L plus h cross Lz A comma Z plus Lz squared A comma Z. Now consider Z is goes to Z maximum. So maximum state, highest energy level. So L squared A comma Z maximum is nothing but L minus L plus operator A comma G maximum operator plus h cross Lz A comma Z maximum operator plus Lz squared A comma Z maximum. Again, this is already in the highest energy level. Again, if the racing operator acts on the highest energy level, it will give 0, only vacuum. L plus operator acts on the Z maximum will be 0. So this term is rewritten. Z maximum is nothing but Lz squared A comma Z maximum plus h cross Lz A comma Z maximum. Now L square operator acts on this state will give eigenvalue as A and the state vector, and Lz twice acts on this state vector will give as Z maximum square comma A comma Z maximum plus H cross. So it's acting once only. So G maximum A comma state vector. Now we can take out, or we can simply write the value of A here. In this case, G maximum square plus H cross G maximum, or we can also write it Z maximum plus H cross is nothing but A. Fine. So the value of A is determined. Now if we look, the L square acts on A comma Z maximum is nothing but okay, from the previous expression, again I am writing one important point, is nothing but L Z square A comma Z maximum, the first term will be 0. H cross L Z A comma Z maximum. I am taking again this expression, and if you look here carefully, the L square acts on this state. We are getting the value this one. We are getting this value is nothing but Z maximum square plus H cross Z maximum. If we are taking this one, so G maximum square A comma Z maximum plus H cross Z maximum A comma Z maximum. This is what we are getting. But if you look this term, I am writing that one here, L Z squared A comma Z maximum, it's giving Z maximum square A comma Z maximum. That means if the total angular momentum acts on this state vector, it's giving Z maximum into H cross, G maximum square plus G H cross. But the total angular momentum along G component acts on this state vector, simply giving G maximum squared. But the total angular momentum L squared acts on the same eigenstate, it gives Z maximum squared in addition to this new term Z maximum H cross. There is one additional term is also coming from this angular momentum algebra. So basically, where this G maximum H cross is coming. In classical physics, if we are taking L squared as L x squared plus L y squared plus L z squared, total angular momentum is a sum of the angular momentum of all the three components, and if all them particle rotating or all the particle is perfectly aligned with the z direction, then Lx equal to Ly equal to 0 and Lz is perfectly along the g direction. Angular momentum on g direction is parallel to this one. Angular momentum is parallel to g direction. Then the total angular momentum is nothing but the angular momentum along g direction. Total angular momentum is equal to the angular momentum along g direction. But if we look here, the measured total angular momentum L square is nothing but G maximum square plus G maximum H cross, but the measured angular momentum along Z direction is only Z maximum squared. So this additional term is also coming. That means in quantum mechanics, L square is not equal to Lz square, or L is not equal to Lz. The contribution of additional angular momentum or the residual angular momentum somewhere distributed in x and y coordinates, but the value of angular momentum distributed in x and y coordinate is very small quantity, and the G maximum H cross is nothing but very small quantity when compared to G maximum square. So fine. Again, there is an equation we have written. L is at angular momentum along z direction and L plus minus a z is nothing but, so it will give you z plus minus h cross L plus minus a comma z. This is what we have already discussed. Okay, fine. Suppose the raising operator or lowering operator acts on a state H cross, Z plus minus H cross, and we are measuring that effect along Z direction, L is it. So what will be the answer? We have already discussed, this is a G vector, component vector is in this direction here, and if L plus acts on this state, we will get it Z plus H cross. Again, if it is L plus acts on this state, Z plus H cross, and what is the effect of angular momentum along Z direction? We have to find out that value here. Let's see. First, take only the raising operator A comma Ez plus H cross, a state vector, is nothing but Lz and L plus A comma Z plus H cross. Now what is the product of Lz L plus? We have already determined the value of Lz L plus is nothing but H cross L plus plus L plus Lz, and A comma Z plus H cross. Now if you multiply inside, L plus A comma Z plus H cross plus L plus Lz A comma Z plus H cross. So if this operator, raising operator, acts on this state, it will give eigenvalue Z plus H cross no, you just keep it in this section. The H plus L plus A comma Z plus H cross, if L plus this Lz operator acts on this state vector, will give Z plus H cross as eigenvalue, and the state vector will be retained. Now this expression, this is nothing but a number, eigenvalue is nothing but a number. We can actually rewrite this equation L plus A comma H cross plus Z plus H cross L plus A comma Z plus H cross. Now we can take it, this is a common term, this is the eigen vector of Lz operator, angular momentum along Z direction. Then we can write it Z plus H cross L plus A comma Z plus H cross. Then finally we can write answer for this Lz operator acts on Z plus minus H cross is nothing but, we can write Z plus minus 2H cross L plus minus A comma Z plus minus H cross. The eigenvalues of Lz operator, eigenvalues of Lz operator LZ operator or quantized. Or the discrete values. From this we can actually clearly see Z plus H cross G plus 2H cross, next G plus 3H cross, next G plus 4H cross, it will be like this. So Z plus H cross, G plus 2H cross, G plus 3H cross, it goes like that. And similarly, while measuring the angular momentum along Z direction due to L minus operator acts on this state is also quantized. So this is a combined mathematical expression for that phenomena. Okay, so now we will actually determine the number of quantized values, quantized energy levels from Z maximum to Z minimum. So this is nothing but Z minimum and this is Z maximum. See example, this is a Z vector here, the next one is Z plus H cross, first quantized energy level, and the second quantized level due to rising operator. So similarly, due to lowering operator, Z minus 2H cross, again if it is Z minus 3H cross, if third time if L minus acts on Z, it goes like that until reaching to G maximum. Here also it goes like that until to reach the Z minimum. Further again, if L plus acts on Z maximum will be 0, L minus acts on Z minimum, that will be again it's 0. Fine. So how many number of quantized levels between G maximum to Z minimum? For that we have to find out Z maximum minus Z minimum. The difference of Z maximum to Z minimum will gives as NH cross. So in general we can write this one, the Z maximum value as Z plus LH cross. L may be any number, real number from 0 to 1. So if L is 0, then we are in this state. If L equal to 1, we are in this state. L equal to 2, then we are in this state. So it will go like that. And similarly, L also having a negative value, L minus 1, minus 2, minus 3 will also be there. So the L will move from minus L to plus L. So then Z minimum we can write it Z minus L H cross. If we feed these two value to this expression, we will get Z plus L H cross minus Z plus again LH cross. Equal to NH cross. So it will give the number of quantized energy level between G maximum to Z minimum. Then if we simplify this one, so we will get it 2LH cross equal to NH cross, or the value of L we can get it N by 2. So example, if L equal to then the value of n is here, integer value and even integer value, and n with odd integer type of angular momentum generally do not happen. So we will concentrate only n with even integer. Suppose put n equal to 0 here, then L will be 0. Then we are in this state. N equal to 0, L equal to 0. If n equal to 1, n equal to 2, then L will be 1. So we are in this state. N equal to 2, L equal to 1. This state. Either we are in this state or this state. Alternatively, suppose the value of L equal to, if we are writing as a 5, then L equal to 5 n by 2 or n equal to 2L, 2 into L 5, there is a 10 number of discrete energy levels will be there. So for example, if L equal to 5, then Z plus 4H cross, and this one Z maximum is Z plus 5H cross. There is one energy level, another energy level, second, third, fourth and fifth. There is 5 energy level in a raising operator and another 5 energy level with the lowering operator. So total number of discrete values or the quantized value in this particular example is nothing but 10. So we can write L is nothing but Z maximum is nothing but orbital angular momentum quantum number, orbital angular quantum number L. Also we call it this as azimuthal quantum number. Azimuthal quantum number. There is also another quantum number called ML is nothing but the magnetic quantum number. Orthogonal projection of the orbital angular momentum vector. So orthogonal projection of this one. Is nothing but ML. So that is defined all the Z values. So the number of Z values from Z minimum to Z maximum. Z minimum to Z maximum divided by H cross. For this particular example, when L equal to 5, then the number of Z values 1, 2, 3, 4, 5, 6, 7, 8, 9, then G minus 5H cross. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there should be ML equal to 11 values. So for writing in general, the ML equal to 2L plus 1. So here there are one group of L, and in the raising operator and the lowering operator the same group of L, but with the lowering operator in addition to the one common level or the vector Z vector. So here this is 2L plus 1, we can write it. So in general, we can write the value of n or 0, 2, 3, 4, 6, it goes like that. The corresponding value of L is nothing but, by using the formula we can find out, this is 0, 1, 2, 3, 4, it goes like that, and the corresponding value of ML will goes from minus L to plus L. So this one is orbital angular quantum number, and this one is the spin magnetic quantum number or the magnetic quantum number. This is simply magnetic quantum number, orbital angular quantum number. Orbital angular quantum number, this is magnetic quantum number. Magnetic quantum number. Can you take some more time? It's okay? Because another 2-3 pages are there. So I will finish it. So as we discussed here, the Z maximum minus Z minimum is nothing but a quantized value with n h cross, but we can also write the Z minimum with a negative sign is equal to Z maximum. This one. This is Z maximum and this is Z minimum. The negative value of Z minimum is nothing but the Z maximum. Then if we feed this value here, then Z maximum minus Z maximum is again Z maximum, or 2Z maximum is n h cross, or Z maximum equal to n divided by 2h cross. As we already discussed, the Z maximum is nothing but the value of L, and this is nothing but L. H cross. This value is nothing but L. But the one equation we have discussed, the value of A is nothing but the Z maximum into Z maximum plus H cross. And similarly, with the Z minimum also we have discussed Z minimum with Z minimum minus H cross. So if we feed this value Z maximum into this equation, then the A will be L H cross, L H cross plus H cross. Then this will be L into L plus 1 H cross square. If we take it H cross, here already L H cross is there, here L H cross plus H cross. If you take this H cross outside, then L into L plus 1 H cross square is nothing but A, or we can write by using this term A equal to L into L minus 1 H cross. We can write in both way, there is no problem. So now we have orbital angular momentum state is written A comma Z. The angular momentum state is combined state is written A comma Z. Now we know the value of here A is nothing but L into L plus 1 H cross square, comma, the value of Z also we know, that is nothing but M L H cross. So G maximum is here we have written the equation. One is M L equal to Z divided by H cross. So from this expression, Z is nothing but the number of Z levels, from Z maximum to Z minimum, that is called Z, okay. And here we can write it M L H cross. So that's what we written here. But writing in such a way looks very odd. Better to write this combined state with the quantum numbers associated with each of the states. So example, in this case, L is quantum number, orbital angular quantum number associated with this term A, and the magnetic quantum number M L is associated with Z, then we can write it simply M L here. Finally, all the state vector, say example L square associated with A comma Z is nothing but the eigenvalue of A and A comma Z. This is a state vector associated with the operator is written in this form. Again, another operator called LAZ operator, A comma Z is also written the value of Z here and A comma Z. And another raising operator and lowering operator is also written like this, C plus minus some coefficient and then A comma Z plus minus H cross is written. But if we are writing in terms of quantum number, we can also write this one. So example here, L square, L comma ML is nothing but, so here A is nothing but L into L plus 1 H cross squared L comma ML. And when we are writing this one, LZ operator, L comma ML is nothing but, the value of Z is nothing but ML, then ML value is nothing but ML H cross. How we are writing here? The G value. So this one is L comma ML. Similarly, when we are writing this one, L comma ML equal to C plus minus L comma ML plus minus 1. Now our aim is to determine the value of C plus and minus. For finding the value of C plus minus. For finding the value of C plus minus, again we had to go with the raising operator and lowering operator. L plus is nothing but Lx plus ILy, and L minus, the complex conjugate of L plus is nothing but ILy. Take the product of these two, L plus L minus, take it the product of L minus L plus, and find the expectation value of L minus L plus with the state vector L comma ML finding the expectation value of L minus L plus in the state vector L comma ML, combined state. Fine. But as we said, the L minus is the complex conjugate of L plus. So if we are rewriting this formula, L comma ML L plus and L plus L comma ML. So this particular term L minus is the complex conjugate of L plus. So if you are writing the bra vector into ket vector. Now, so this one we can write it L plus L comma ML determinant square, simply. But if we look this equation here and take square of this equation also, L plus minus operator L comma ML is equal to C plus minus L comma ML plus minus 1. Take the square on both sides. Now if you compare the equation, these two, this and this is nothing but this one. Then in place of this you can put this one. So I am writing L comma ML, L minus L plus L comma ML is equal to this one, but this is nothing but C plus minus, because it's a constant, so we can write separately, there is no problem. So L comma M L plus minus 1 so if we are writing C plus minus determinant squared, this will be 1 normally. Again L comma ML plus or minus 1, L comma ML plus or minus 1. So this will be 1. The value of C plus minus determinant square is nothing but L comma ML, L minus L plus L comma ML. So now we have to sort out this problem. What is the value of L minus L plus? So this L minus L plus is nothing but L comma ML. Already we have find out L x squared plus L y squared minus h cross L z, L comma ML. We have already discussed this one. Then but the total angular momentum L squared is nothing but L x squared plus L y squared plus L z squared. Or we can write this one, L x squared plus L y squared is equal to L squared operator minus L z squared operator. So if we feed this value here, then C plus minus square is nothing but L comma ML, L squared minus L z squared minus h cross L z, already there that term here, ML. Okay, fine. But the value of L square is nothing but, we have already discussed. So the value of L square is nothing but value of L square is nothing but L into L plus 1 h cross square, and value of L z also is nothing but M L h cross, and L z square also M L square h cross square. If we feed all these values into the above expression here, then C plus minus determinant square is nothing but here L comma ML, So L into L plus 1 H cross square and L comma ML, only if we are taking the inner product with L square. So then minus again L comma ML. L Z squared is nothing but ML squared H cross squared, again L comma ML, again one negative sign is there, minus H cross L comma ML, and LZ is also ML H cross L comma ML. If you look this expression, all these values are only just a number. This is also a number, this is also a number, this is also a number. We can take that numbers outside. Simply take all the numbers outside of each of the expression. So L into L plus 1 H cross square, then L ML and L ML only will be there, inner product of this two vector, minus similarly here also M L squared H cross square again L comma ML L comma ML, then minus M L H cross L comma ML L comma ML. So all these values will be 1. Then C plus minus determinant squared is L into L plus 1 H cross squared minus M L squared H cross squared minus ML H cross. Then this one L into L plus 1 H cross squared minus it might be already one H cross squared is there here. So this will be ML H cross squared. So ML H cross squared. Then we can take out 1 ML and ML plus 1 H cross squared. If you multiply with a negative sign, then ML squared H cross squared, then ML H cross squared with a negative sign, we will get it. So again, if we are reducing L into L plus 1 minus ML into ML plus 1 H cross squared as a common term. Then if we remove the square, this is only for C plus, not for C minus. We are only finding for C plus. Then C plus is nothing but H cross square root of L into L plus 1 minus ML into ML plus 1, the value of C plus. If we are placing the value of C plus from here to here, then we can also write L plus operator acts on the quantum state L comma M. L is equal to H cross square root of L into L plus 1 minus M L into M L plus 1 C plus only. Then L comma M L plus 1. Similarly, we can also write for L minus operator with the quantum state L comma ML is nothing but H cross square L into L plus 1 minus M L into M L minus 1. Here there is a difference with L comma M L minus 1. So we can write by combiningly L plus minus operator L comma ML is nothing but H cross square root of L into L plus 1 minus M L into M L plus minus 1 L comma M L plus or minus 1. So that's it, finished.